Good afternoon to all. So my goal for today is just to provide an overview on the resources available serving metabolomics needs here on campus. So I'm going to spend a little bit of time highlighting some instrumentation, some applications, and then of course we can have some discussion at the end. Just so everyone's aware, we are recording this. So my goal today is to talk about metabolomics, and to make sure we're all on the same page, I just want to start by defining that term. Metabolomics is an analytical approach, primarily using mass spectrometry, where we're trying to characterize all of the small molecules, generally in biological samples. Broadly speaking, there's two flavors of metabolomics, untargeted and targeted. With an untargeted application, we're generating extracts from a sample in a general solvent system, trying to make sure that we have relatively rich samples. We want to detect as many things as we can, so we want to extract as many as we can. We then analyze this extract on an instrument which detects the maximal number of metabolites. Generally speaking, this is done on a time-of-flight or an Orbitrap instrument because they offer high mass resolving power and mass accuracy, which we'll spend more time talking about later. And then we annotate those signals and use signal intensity as a surrogate to approximately, or to provide relative quantitative data. So we can see how the metabolite concentrations are changing, even if we don't actually measure the actual concentration. Alternatively, there's targeted metabolomics, where we typically would try to optimize sample prep for particular analytes. For example, if we want to measure phytohormones, we can use a solvent system that we know extracts them well. We then optimize the data acquisition on the instrument, which then we collect data only on the signals of interest. Generally, this is done using tandem quadrupole or single quadrupole mass spectrometry, where we're using the quadrupole to isolate only those ions that we are targeting. And then we process the data only for the signals of interest. There are hybrid versions. In fact, I'll tell you an example of this later, where we can collect untargeted data. That is, we use a general extraction system, we use a general data acquisition system, but then we process the data in a more targeted fashion. Most of what I'm going to talk about today is untargeted metabolomics, and it has really an approachably impossible goal of trying to measure everything. And it's impossible because metabolites are extremely diverse. They're very small, they're very large, relatively speaking. They can be very polar and very nonpolar. They can be extremely concentrated and extremely dilute. And so there's no one method to really quantify all the metabolites or even detect all the metabolites in a given sample. But what we want to do is detect as many as possible. And we do that by using multiple platforms. Depending on what sort of analytes you're interested in, we might use liquid chromatography. These tends to be really well suited for larger small molecules, where we can use a halic column for polar metabolites, or we can use a reverse phase column for nonpolar metabolites. Sometimes we'll use gas chromatography instead. Gas chromatography is extremely well suited for the analysis of volatiles, because the mobile phase through the column is a gas, and therefore gases move with the mobile phase. We can also analyze semi-volatiles because we can increase the oven temperature in which the column resides to get the semi-volatiles into a volatile state to move through the column. And we also sometimes analyze non-volatiles, such as amino acids and mono and disaccharides, with gas chromatography following derivatization to make them more compatible with GC-MS. On the back end, we can use mass spectrometry to detect the analytes coming from the column, and then to also use the mass spectrometry data to help characterize them. So generally speaking, with gas chromatography, we have a quadrupole at the end, sometimes a tandem quadrupole, and sometimes a time-of-flight. And with liquid chromatography, we're almost always dealing in an untargeted world with time-of-flight and Orbitrap data. Further, we're often trying to acquire MSMS data, and this can be done using different acquisition methods, including data-dependent acquisition, DDA, data-independent acquisition, DIA, and sometimes supplemented with ion mobility, IMS. We do have talks on our YouTube site that cover some of these topics in more detail, and I can point you to that site if you can't find it. I just wanted to go over quickly the full suite of instrumentation that I would consider compatible with metabolomics as far as mass spectrometry within the ARC. We have 5 GCMS systems, including a GC quadrupole with a liquid autosampler, a GC quad with headspace or SPME autosampler, a tandem quad GC, a GC with a thermal desorption autosampler, which is great when you want to sample volatiles and bring them back to the lab. And we also have an Agilent GC coupled to a Q-TOF. On the LC side, we have an Agilent UHPLC Q-TOF system, a Waters UHPLC Q-TOF. We have a Synapt G2SI ion mobility enabled Q-TOF. It's an interesting instrument. I'm not going to talk too much about that today, but let me know if you have interest in ion mobility. We have a tandem quadrupole coupled to LC, which we use for targeted work. And we also have a multireflectron time of flight, which is a more performant Q-TOF, recent acquisition. And in particular, it's these 3 instruments today that I'm really going to spend most of the time talking about. 2 of them because they are relatively new platforms for us, and the third because we've got all sorts of new assays to highlight. So I'm going to start by talking today about our this interesting instrument. It's a gas chromatography system, Waters APGC, coupled to a Q-TOF. And what you can see, let me select my laser pointer here, is on the right side of this instrument is the gas chromatography system. And on the left side, we actually have a liquid chromatography system. In the center is the quadrupole time of flight. And we can actually change the ionization source here so that it either supports coupling to the GC system or the LC system. And we have options as to which we choose. We can switch back and forth relatively easily. I'm going to talk today primarily about its functionality as a gas chromatography quadrupole time of flight system. And Jeff Nelson, who is pictured here on the right, is one of the employees at ARC that really helps to move services on this instrument forward. So the GC-coupled Waters Q-TOF is first a gas chromatography system. And as I mentioned before, that's really suitable for analysis of volatiles and semi-volatile analytes. This is coupled to the mass spec via an ionization source called atmospheric pressure chemical ionization. This has some unique attributes for coupling to gas chromatography, which make it a pretty exciting platform in my mind. APCI, as this is abbreviated, is a soft ionization technique. What that means is we see relatively little fragmentation and a much, much stronger molecular ion than traditional electron impact, which is most of what GC ionization is. So all of the signals that were spread across many fragment ions are now concentrated into one stronger molecular ion. It offers complementary selectivity to electrospray ionization. So if we have used this instrument quite a bit for in supporting molecular weight analysis, accurate mass assignment, for some of the synthetic chemists on campus where we can't ionize something by electrospray and it ionizes really well using this APGC system. One of the downsides of soft fragmentation is that we have to use dedicated experiments, MSMS, to fragment these when we want to support structure annotation. But it's really cool because it has similar ionization behavior to electrospray. And so we can get ionization where we have a strong molecular ion with accurate mass data. And so a lot of the analytic or the informatic tools that have been developed for LC coupled HRMS, high resolution mass spec, can be used for supporting informatics on this APGC system. Finally, the Q-TOF is an accurate mass instrument. So we have a quadrupole time of flight hybrid instrument, and we can, this specs out at about 5 ppm mass error, which is quite good, particularly for small molecules. That's very good. When we're talking about gas chromatography, compatible compounds, they tend to have molecular weights relatively low, which makes that 5 ppm really, really valuable. And of course, being a Q-TOF, we have MSMS capabilities. So we can either run targeted MSMS experiments or a data independent acquisition mode called MSE which is MS of everything. So we fragment everything all the time. I just wanted to highlight a little bit what this looks like for those with chemistry interests here. This is a schematic of the instrument itself, where you have a GC column coming out the GC in this transfer line, this sort of dark gray blob here, cylinder. And there is a makeup gas or a sheath gas, which comes in around the column. And so the mobile phase on this is not helium as it is on most GC systems, but it's actually nitrogen. And the makeup gas is also nitrogen. So as the compounds are eluting from the column, they flow into this ionization chamber in the presence of a lot of nitrogen. There is now a corona pin here where a voltage is applied, which generates a nitrogen plasma, and is that nitrogen plasma that generates ions. Those are then drawn into the mass spectrometer through the sample cone. So everything behind this point is under vacuum to the left. Everything to the right of this point is at atmospheric pressure, hence AP. Now there's two ways that we can actually run this. We can actually run it in dry mode or wet mode. We'll start with dry mode, and it's described here. So basically what happens is when you form this nitrogen plasma, you get nitrogen radicals formed, which can abstract an electron from your analyte of interest to generate a radical cation. Now, what we can also do is introduce a polar vapor, such as methanol or water, into the source, such that the nitrogen radicals ionize the polar vapor, water vapor, or methanol vapor, and that can induce proton transfer reaction so that we get protonated species. And the example here, this is from Waters' document, shows a polyaromatic hydrocarbon, fluoranthrene, where you actually see a mixed ionization. You can see a radical cation here and a protonated cation here. And so we have control over this to a large extent as to which one we see by deciding whether we want to introduce moisture into the ionization source or not. So I wanted to pick a compound to highlight how this differs from a traditional GCMS system. So this is caffeine. If you look at caffeine in the NIST electron impact library, this is how the spectrum looks. The 194 ion here is the molecular ion. And in this case, you still see quite a bit of it. That's not always the case, but it does happen when the molecule is stable enough. And then we see fragment ions. So all of these are happening as ionization occurs. This isn't precisely an MS-MS experiment, but we get a good deal of fragmentation. This is what the MS spectrum looks like on our system for caffeine in dry mode, where we see a strong molecular ion at 194 and very little fragmentation outside of it. And further, we have accurate mass data. So we have 194 point with several decimal points, and those decimal points are meaningful. So this is what dry mode looks like. And then if we introduce a methanol vapor into the source, we get a similar spectrum, except the mass is shifted by about 1 mass unit because this is now a protonated adduct rather than a radical cation. And so if we were to run caffeine on our LCMS system using ESI, this is the same mass that we would see, same pattern. Now, what's interesting about this is since we do have an MS-MS system here, we can fragment those. So if we fragment then our dry conditions where we have the radical cation, this is the spectrum we get. And you see all of these fragmentation products, all of which are measured with accurate mass. Compare that to the NIST spectrum we saw before, and you can see that a lot of the masses are actually the same. We see a 165 ion here in our spectrum. We see a 165 in the NIST spectrum. We see a 136 to 138 in our spectrum, and we see a 136 to 138 in theirs. Major 109, major 109. So a lot of these spectra are pretty similar because they're both radical fragmentation mechanisms. So what that means is we can take these MSE spectra from our dry mode and potentially search those against the NIST library to help support annotation. Though in addition, we do have accurate mass, which becomes interpretable as well, in a way that low resolution masses aren't. We can do the same with wet mode. So when we fragment our protonated species, our 195, we can see a 138, a 110. And when we compare that to the fragmentation spectrum from the NIST MS library, which is derived from electrospray Q-TOF from an LC type system, You can see we've got our precursor ion, we've got our 138 here and a 138 here. We have a 110 here, we have a 110 here. Even some of these smaller ions, we have the 83 and the 69 down here in our spectra as well. And so what that means is from the same instrument, we can get MSMS spectra that are suitable for searching against either the GC-EI library or the LC-ESI MSMS library, which is kind of cool. Now, I want to highlight one of the applications that Jeff has been developing on this for a client. And so we were interested in measuring polyaromatic hydrocarbons. These PAHs are combustion byproducts, and they have health and environmental detrimental effects, which prompt people to be quite interested in monitoring them. And so for this particular assay, we are targeting 16 analytes, which are on the EPA list of targeted polyaromatics. We've put together a quantitative assay using isotopically labeled standards. One of the nice features of this instrument is we do have really strong linearity, so good dynamic range. We've got a 1,000-fold concentration range that we can quantify over. And this is just the calibration curve for two of the analytes. One is the fluoranthene that we saw in the Waters example earlier, and then this second compound, dibenz AH anthracene, showing nice linearity and strong R-squared values. Now, what's really cool, though, is we're getting really good limits of detection. So our limit of detection on this assay is in the high parts per trillion, less than 1 nanogram per mil. And what's fun about this is it's actually the case using fully untargeted acquisition. So we're doing full time of flight scanning so that we get all of the masses for everything all the time, and we're still getting high parts per trillion sensitivity. So if we had to get more sensitivity, there's actually some tweaks that we could be doing to make that happen. But we're really happy with the sensitivity that we have, and it's fully untargeted. Now, what that means is since we have fully untargeted data, that means we can use untargeted data processing methods as well. So for the assay, we've been doing very targeted data analysis, but it doesn't have to remain that because all of the data is available. And so what this means is we can start thinking about this platform as a really nice platform for exposomics, non-target analysis, environment monitoring, where we're analyzing a lot of these semi-volatiles that are of interest for environmental and health reasons. So this is just an example of a real-world sample to show you how rich the base peak ion chromatogram is. There's a lot of peaks here beyond the 16 polyaromatics that we're interested in. And we have accurate mass data and knowledge of the samples to help support annotating what those are, which is really cool. This is just one example. So if we look at this top chromatogram here, this is an extracted ion chromatogram for the molecular ion for that dibenz anthracene molecule that we showed before, a molecular weight of 278.109 as its radical cation. This peak right here, labeled as such, is the one that we're targeting for the assay. And we see about another 16 or 17 peaks here that all have the same mass, which our assay is not targeting, but we have strong evidence that there's a lot of isomers of this thing that we have the ability to detect and potentially further characterize. And this is just an example for the internal standard for that particular analyte at the bottom. So our next steps for the APGC are to really expand our understanding of the ionization methods. So this polyaromatics is where we started, but we've also been running some pesticides and some phthalates. And really what we want to do is get a really firm understanding of the ionization behavior in wet versus dry mode, and some of the parameters that we can change with it so that we can make some informed decisions on, one, how to acquire data, and two, how to interpret it once we have acquired it. And then we also want to ultimately expand and develop an informatic workflow for this platform so that our users can fully mine the untargeted data that's available through it. Our next instrument is called the XevoMRT, and this is work done with Nathan Montgomery, who manages this instrument. And I will spend a little bit of time talking about this instrument first because it is pretty unique and has some really nice attributes for metabolomics type applications. So we're coming from the Xevo G2XS, and this is actually the Q-TOF I'm showing you here is the one we have on the APGC. And so it's a really nice instrument. But over the past few years, Waters, the manufacturer of this instrument and developer of it, has been making some really impressive improvements. So in 2021, they released at ASMS an instrument called the MRT, Select Series MRT. And this MRT stands for multireflectron time of flight. I'll show you what that looks like in a little bit. But the cool thing about this instrument is that with this multireflectron time of flight, they've got approximately 10 times the resolving power, about 300,000 resolving power, compared to what we have on our standard instrument. And with resolving power, we gain potential for mass accuracy, and they realize that potential, reporting 200 parts per billion mass accuracy on this instrument. Now, this is a really high-end research-grade instrument. It's not necessarily a high-throughput platform. In fact, the first time they released it with a DESI imaging source rather than an LCMS, because it was really well suited for that. That being said, they have since adapted some of that multireflectron time of flight to release this XevoMRT mass spectrometer, which is a benchtop version, still has multireflectron time of flight, with some specs that more closely align with the metabolomics field. So the resolution is not quite as high. We're at about 100,000 resolving power on this one. We still get very good mass accuracy, though, at 500 parts per billion. So we're in the sub-ppm mass accuracy range. But what's a big step up from the Select Series MRT is this particular spec right here, this 100 hertz. So you can actually collect up to 100 MSMS per second on this instrument, which is much faster than you can do on either the MRT Select Series or our older G2XS. And so I'll explain the importance of that as we go. And just for a point of comparison, because I know there's some analytical junkies in the audience, the 21 Tesla FTICR system, one of the highest resolving instruments in the world, can obtain almost 3 million resolution, which is quite a bit higher than what we're getting, of course. Parts per billion, 80 parts per billion mass accuracy. The trade-off there is that oftentimes your scan times are in the order of 6 seconds. And so if you're doing metabolite studies where you actually need to use LC for separation or GC, it's not easily coupled to a chromatographic dimension. And obviously this is a multi-million-dollar instrument, and the rest of these are not. So they all have their strengths, they all have their weaknesses, but the instruments that we have here in the lab right now is really exciting for lipidomics and non-targeted metabolomics and exposomics type applications. So this is what it looks like in spec. And basically what we see here is we see the front end of the instrument over here on the left, where we would have the LC coming in from this analyte spray. We have something called a lock mass spray. This helps us to maintain mass accuracy over long time periods. And when I say long time periods, I mean through this we can get mass stability over weeks and into months. There's an isolation valve built in here. The step wave ion guide takes the high gas flow from the ionization source coming from high pressure under low, and it traps the ions. It raises them in this step pattern here so that neutrals are drawn out. The step wave then transmits the ions to the quadrupole. We go through this particular lens. It's called a DRE lens. Into a collision cell where we can fragment, and they have this particular focusing region here. I think that they've put a lot of development both into the collision cell and the focusing region to get really good sensitivity and duty cycle, which I'll describe a little bit later on. But this big block that you see back here on the end is really the highlight of the instrument in some ways. That's a multi-reflectron time of flight. So they use these gridless mirrors so that they can reflect back and forth across these mirrors several times. And I think that this is a 10-pass instrument. The floor model MRT can be any number of paths. So it can bounce back and forth as many times as you want to a certain extent before it hits the detector. And this is important because the longer the flight path, the more resolving power you have. And so they've done a lot of engineering to get ion packets tightly delivered to this pusher region, get several reflectron passes through here to get resolution in the 100,000 range with still very good duty cycle and sensitivity. So if we think about the specs I'm talking about, why am I so interested in mass accuracy? And if we look at PubChem, which is a massive structure database, there are approximately 7.6 million unique molecular formula for about 120 million unique structures. So it's a very big data set. If you look at the molecular weight range distribution of the analytes in here, you can see that there's a lot of them below 500. And then the distribution sort of falls off toward the higher mass region. Not necessarily because those molecules don't exist, but because we haven't characterized them well enough at the lower end. But if you look closer and you just zoom in on one particular region, you can see that this distribution isn't as smooth as that first plot looks. So if we look at this 454 region, you can see that there's a lot of masses formula around 454, and then there's a lot around 455 and 456, but there's a valley in between them. And so really what we do with mass resolution is we try to separate as many of these in any one of these peaks as possible. The more resolution we have, the better we can do. And so let's look at one example. So this is a compound called verapamil, which I was able to get a spectrum from Waters from their MRT instrument pretty early in their process. This is the molecular formula, and here's the monoisotopic mass, 554.2832. So that sits right about here in that distribution. And you can see there's a lot of other things there. So this is an MS-MS spectrum from that instrument. And if you look at the precursor ion, the 455 M plus H, this has about under 0.2 ppm mass error, which is great. And all of the fragment ions also have a similar mass error, since all of the MS-MS data is collected under the same TOF conditions as the precursor. Now, what you can do is you can look at all of the formula in PubChem, and you can say, for all of the formula, plot their monoisotopic mass, and I plotted it as this vertical line here. So every one of these vertical lines is a formula at its accurate mass. Now at 5 parts per million mass error, which is this bar right here, you can see that there's about 35 formula that it's consistent with. At 0.5 ppm mass error, there's only 2. And so by increasing the mass resolving power and the mass accuracy, we can be much more confident when we're assigning a formula to this analyte. We've narrowed it down to 2 using just the MS accurate mass alone. Now let's make an assumption that all the fragment ions are also formula in the PubChem database, and in this case, that's actually true. You can find formula representing all of these in PubChem. And now if we look at the fragment ions for 165, and we look now at all of the formula in PubChem in that mass range, you can see again at 5 ppm, we probably have about 7 or 8 formula that are consistent. At 0.5, we have only 1. And it turns out that this one formula is only a subformula of one of these 2. And so with the combination of accurate mass on the precursor and accurate mass on the product, we can narrow down the formula to this one particular formula, the correct formula for verapamil in the PubChem database. So we can get a lot of confidence, not only from the accurate mass of the precursor, but that of the product as well. That was one example, not a cherry-picked example, but one example nonetheless. And so I did a similar study with predicted spectra, looking to see how much can we really use this. And if we use some of our computational tools, in particular the Sirius program, how often can Sirius get the right answer given an unknown spectrum as far as assigning the correct formula as a function of mass error? And as our mass error goes down, you can see on this pink line that the proportion of correct answers goes up. And so at about 0.5 ppm, we're at about 75% of the time it's returning the right answer for the correct molecular formula. And if we consider the formula, the right answer being in the top 5, we're up to about 85%. And so what this tells us is that, one, not only can the mass accuracy be valuable for manual interpretation, but also for computational. And that's really exciting because there's a lot of compounds in PubChem, but Sirius isn't purely dependent on that. It can be using data from anywhere, including proposing new structures. And that accurate mass data can be valuable in improving the accuracy of those processes. So that's mass accuracy. Another parameter that we're really interested here is speed or duty cycle. And so this is an example of, this is a figure from Waters showing their collision cell up here, and so they've re-engineered that to make it faster, effectively. And so what we have on the bottom plot here is an older instrument. They are highlighting the Xevo G3 Q-TOF. Ours is the G2, the one that we had before, and that is on the APGC. This is at 30 hertz. So if you're collecting 30 MSMS per second, this is the pattern of what that would look like. You would collect a spectrum, and then there would be an interscan time. That's what the white spaces between are. Spectrum, interscan delay, spectrum, interscan delay. And what you'll see, comparing the green on the bottom to the blue on the top, is that there's much less white space. That's because the interscan delay between the instruments has been decreased from about 14 milliseconds to about 2 milliseconds. Now, what that means in practice is there's a lot less white space and a lot more blue. What that blue is our duty cycle. And so if we're collecting 100 MSMS spectra per second on the XevoMRT, we have a duty cycle of about 80%. On the older instrument, at 30 hertz, our duty cycle was about 58%. If we got up to 100 hertz, it would be more like 20%. And so the speed of the MRT has been increased, not only for the acquisition itself, but reducing the wasted time, so to speak. And what that means is we can collect a lot more MSMS data much more quickly. And so if we think about the properties of our MSMS acquisition, in particular, we'll use data-dependent acquisition. The ideal properties are that it's fast. The more spectra that we can acquire, the more confident annotations we can make. The second is that it needs to be selective. We want to isolate the precursor ion in a complex sample from all the other ions to generate an MSMS spectra which is as clean as possible. We then want it to be sensitive. Fast is great, but if we don't get good generation of ions, fragment ions, and transmission of fragment ions to the TOF, then that speed isn't really of value. We don't need to generate 100 bad spectra per second. We want to generate good spectra. Finally, we want to take advantage of that accurate mass. And one of the nice things about a time of flight is that there's no trade-off between scan time or speed and mass accuracy. So that's one of the properties of a time of flight, which makes it particularly amenable to fast analyses. And so here's an example of highlighting some of these properties on this instrument from a lipidomics example. And so this is just an MS spectrum from one particular sample at one particular point in the chromatogram. And what you can see here are several lipids, all eluting from the column at the same time. And through DDA analysis, the instrument selected the 760 ion, which you can see right here in the MS spectrum, to generate a very nice MSMS spectrum, which shows us a 184 fragment ion, 184.074 to be precise, which tells us that this is a phosphatidylcholine lipid. This is a MSMS spectrum. You can see resolution specs here over 1 million, and we're getting mass accuracy that's the same in the precursors, the product. One other thing I want to point out here is that you can kind of see there's a little shoulder here, and there's a little bit of shoulder here. Those are isotopes at 761 and 762. We've isolated them here. So 760 was sampled, but the isotopes are not. So our quadrupole that is doing the precursor selection, we've reduced it down so that it's only acquiring the isotope of interest. And what that means is we have less chance of contaminant ions being found in the spectrum when you have a lot of things coming off the column at the same time. And so but we're keeping sensitivity while doing so. So there's often been a trade-off in the past, and on this new system, there's much, much less of a trade-off. The sensitivity is quite a bit better, even when we're being very restrictive on the quadrupole. Now, if I zoom into that 760 region, here you can see those isotopes. So we've isolated them on the precursor and fragmented them. But the exciting part for this instrument is not that we can sample that relatively intense item well. If you look now at some of the lesser signals, there's another signal here at about 758.5, and we can still get a good MSMS spectrum for that, identifying this as yet another phosphatidylcholine with a nice prominent 184 and a very clean spectrum, even though that this signal down here at 759 is only about 2% of the signal up here, and this is a 50 millisecond scan. So the speed that we're using to acquire these MSMS is great, but it wouldn't be valuable without the sensitivity and selectivity, and we're still able to get both of those, even at 20 hertz in this particular test. So our next steps for the XevoMRT is to really optimize DDA so that we can come up with some good rule sets to make sure that we're really optimizing how many high quality spectra we can get in a particular sample analysis time. So we have options that we can consider, including the acquisition speed of the MSMS. We can range this from 10, 20, 50, or 100 hertz. That is 100 MSMS per second. So 10 millisecond scan times. And that's extremely fast, and we may be able to sample a lot more things that way. The question is, are the data quality of sufficient to annotate things with confidence? And so we want to explore these in a little bit more detail with some real biological samples so that we can have some good base methods from which to start from whenever any of you come to us with new sample requests. Another question we have is how much time can we dedicate to MSMS if we also want to keep good MS data quality? Things like collision energy, what's the most appropriate value, does depend on the types of compounds, and this is more difficult to do generally, but it's something we need to explore as the collision cell is a little bit different than the one we've had in the past. And then we also want to compare to MSE workflow data independent, which is what we've been using in the past. And then finally, we want to make sure that we've got good informatic workflows to take advantage of this. So historically, we've been using MSE a lot. And now we have DDA data. And so we want to make sure that we're using all the best practices to make sure we're taking as good advantage of this as possible. I do want to highlight that we do have a lot of informatics experience in the group. So I personally work heavily in R. So our R-based workflow is very well developed. We have a lot of options, some of which we have standard workflows, some of which is easily adapted to other workflows. So if you have questions about what you could do, just reach out and I'm happy to discuss. But our standard workflow, we're processing data using a program called XevoMRT, which detects signals, aligns them across samples, and can do other pre-processing workflow steps. Then we use a product called RAMClustR, which we wrote here at CSU, which calls a program called Interpret MS Spectrum. And what these do is it groups features from XevoMRT and annotates those features to say, does this look like a sodium adduct or a potassium adduct? Is this an isotope or the monoisotopic peak? And what's the charge state? Then there's been a lot of development over the past couple of years in what's called a meta package called R for mass spectrometry for base level handling of spectral data, spectral searching, compound libraries, compound annotation. There's a lot we can do there. And really, I would say the sky's the limit as to what you could do there for customizing a workflow for your needs. More recently, I put together an R package called pubchem.bio. This is something I developed in part out of necessity. We run a lot of different metabolome analysis for a lot of different people with a lot of different species. And it'd be great to have a metabolome-dependent, a species-specific metabolome database for all of these. So I spent a lot of time over the past several years building these by hand, and I realized there was a better way to do it using data from PubChem. And so what this enables, this package, is it enables us to generate a species-specific metabolome database for any species that you can imagine. And it uses something called taxonomic proximity scoring. So if we've got metabolites that are taxonomically mapped, we can actually use that mapping in our scoring threshold to prioritize spectral matches and such. And we have a dashboard to explore some of the data from this. And then, of course, R is really well-versed, well-built for statistical analysis. Pretty much anything you might want to do as far as statistics, you can do in R. We do have a lot of other software that we use too, which I want to highlight. So for targeted data analysis, even of time-of-flight data, we're often using Skyline. We can do a lot of the work that is done through XevoMRT and RAMClustR through MZMine or MSDial. Those are graphical user interface type programs, which can be a little bit easier for some folks to learn if they're not comfortable in R. There's computational tools such as Sirius and MS Finder. We've used those a lot. We have the NIST MS and MSMS spectral library. And there's a new tool out that I've been using quite a bit called Fiora, which can actually predict MSMS spectra for any structure. protonated and deprotonated adducts, or the current model train predictions. And now I want to highlight some of the targeted applications, and really this is work done primarily by Lin-Sing Yao and working with Grace Heinrich. And the instrument pictured here is a UPLC tandem quadrupole. So on the left is our UPLC system. This looks very similar to some of the other instruments I've showed you because it's the same manufacturer, same ionization source, same LC, same column. It's just that it's a tandem quadrupole, which makes it very well suited for targeted analyses. And I'm not going to go into a lot of depth on any of these or tell any great stories, but I just wanted to highlight that there are many assays that Lin-Sing and Grace have developed over the years. And I just wanted to highlight some of these. These include phytohormones, B vitamins in grains, biomarkers for glomerular filtration rate, choline metabolites, cannabinoids, oxylipins, et cetera, et cetera. That's about half of them. And then there's another one here. And there's more, actually. So some of these are very common: fatty acids, amino acids, mono and disaccharides. Some of them you can imagine are very specific. And the reason that we have so many assays is because we are developing these for people that ask for them. And Lin-Sing is pretty efficient about doing so. And so if you see assays that you would like to have run that is not on this list, that doesn't mean we can't do it. We develop custom assays with some regularity. And this is a list of the assays, but I just wanted to highlight how extensive some of these are. And I just picked 3. The oxylipin assay, I think, has about 35 analytes, maybe it's more. And so these are signaling molecules in mammalian systems, oxidized products of lipids that have big roles in stress and stress signaling, and often in disease, actually. There's a panel for NAD, NADPH, NADP metabolites in blood. And so this includes a lot of the analytes that are metabolic precursors and products of NADP and NADPH. TCA metabolites. And so these are all assays that are available and developed. Some of them are relatively focused and targeted. Some are larger. And so they're all available, though. If you see anything that strikes your fancy, reach out. If you see anything that you wish we had, let us know as well. There's the opportunity for custom development. I also wanted to highlight a nice application that Lin-Sing's been participating in with a researcher here in town called Biocrates. And this is effectively a metabolomics kit that is used for sample preparation. And so it's really designed primarily for blood analysis, mammalian blood type samples. But there's some opportunity to adapt it. And basically what it is a sample preparation kit that comes with columns and methods and internal standards and processing software. And so you prepare your samples, often in a plate-based format, and then we acquire data on our LC tandem quadrupole system, and that data is uploaded to their software for data processing and analysis visualization. And so what this provides is extensive pathway coverage. This particular kit that we're using has over 1,000 metabolites from 39 biochemical classes. And one of the cool things, if you don't want to spend a lot of time rebuilding the wheel, is their software is actually mapped a bunch of these metabolites to pathways and disease health state indicators, so that there's a lot of opportunity for some built-in interpretation that sort of comes with the kit. The kit isn't cheap necessarily, but it is a value in that it provides a lot of these links, and it also provides quantitative data on all of these analytes. So generating an assay that can provide quantitative data on up to 1,000 metabolites is a tall order. And so they make this feasible through this kit that's available as well. I also just wanted to highlight some of the other areas of the lab. Jackie Chaparro on the left provides analysis of metals and minerals. So she's going to be providing a seminar, I think next semester, on application of this for food analysis, looking at metals and minerals in foods. Gustavo Diaz here in the center runs our proteomics and metaproteomics using our Orbitrap platform. And I wanted to also mention Claudia Boot, who runs many of our walk-up instruments for metabolomics, GC and LC systems, with Paul as well in the ARC-MMA area. And I also wanted to mention that Claudia has done a little bit of work developing methods for NMR-based metabolomics as well. So in summary, we have a couple of new instruments, the XevoMRT, the multireflectron time of flight, really nice mass resolving power, really nice MSMS acquisition speed and sensitivity, and excellent mass accuracy make this a really a pretty incredible platform for characterizing complex samples with really high quality data. This G2XS, Xevo G2XS APGC system is a pretty unique system where we can get accurate mass MS and MSMS data on a GC coupled instrument. And I see a lot of opportunity here for developing some custom environmental type applications, such as the polyaromatics that I described before. But I think that it's also got a ton of opportunity for applications in the untargeted world. We have strong informatics options and support for whatever you want to do. And so it's an area that I've spent a lot of time thinking about. And if you've got things that we don't do that you'd like to do, I'd still be happy to talk about it because I've probably thought about it at one point or another. And if I haven't, I'm excited to learn about it. And then finally, I wanted to highlight some of the targeted metabolomics options. We have a lot of existing panels that are available, many of which are absolute quantitative panels. And we also have the ability to implement new assays for you at your request. And finally, I highlighted the Biocrates kit for targeted quantitative metabolomics. And with that, I will open it up for questions.